I am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this lecture series, we are going to see the topic dielectric boundary conditions for the unit dielectrics and steady electric current. So, the boundary conditions are very important because practical electromagnetic problems often involve media with different physical properties. So, the determination of electric field for such problems requires the knowledge of the relations of the field quantities at an interface between the two different medias. So, the conditions that the fields must satisfy at the interface of the two different media are referred to as boundary conditions. So, in the diagram we are taking a perfect dielectric material, two materials having different permittivity values. So, medium 1 is above horizontal line, medium 2 is below the horizontal line. So, for this we are going to obtain the boundary condition. So, on the left side we are closing with pillbox having the width del W and two electric fields E1 and E2, and the height of the pillbox is del H. And at the right side we use Gauss law to determine the normal component, and it is closed by a Gaussian surface with two normal components AN1 and AN2 and the two displacement density vector D1 and D2. So, the first diagram, the left hand side diagram, is used to obtain the properties of tangential component of electric field, and the next right hand side diagram, the Gaussian surface is used to obtain the normal component relationship of a dielectric materials between the boundary. So, now we can express the electric field in terms of the tangential and normal components are E1 vector by E2 vector is equal to E1 1 2 vector plus E1 1 2 vector, and also E2 vector is equal to E2 1 vector plus E2 n vector. So, here the Et is called tangential component, En is called normal component of electric field intensity. So, both the E1 vector and E2 vector is obtained by adding the corresponding tangential component and also normal component. So, around the closed path on the left hand side pillbox diagram, we have E tan 1 del W minus E tan 2 del W is equal to 0. So, a small contribution to the line integral by the normal component of E along the sections of length del H becomes negligible because del H decreases, the closed path crowds to the interface. So, we can get E tan 1 is equal to E tan 2, and from this we can say that tangential component of electric field is continuous across the boundary. So, that is below the boundary and above the boundary, the tangential component of electric field is same, both are equal. And the tangential component of electric field is continuous across the boundary. Now we are going to find out the tangential component of electric flux density D. So we know the relationship between D and Es, D by epsilon is equal to E. So we can write that D tan 1 by epsilon 1 is equal to E tan 1 is equal to E tan 2. E tan 2 can be written as D tan 2 by epsilon 2. So finally we can conclude that D tan 1 by D tan 2 is equal to epsilon 1 by epsilon 2. So we can say that the tangential component of electric flux density is discontinuous across the boundary because D tan 1 is not equal to D tan 2. Here D tan 1 is equal to epsilon 1 by epsilon 2 into D tan 2. And now we come to the next diagram, and we use Gaussian law in order to find out the total surface. So, for getting the relationship between the normal component across the boundary, we use Gauss law. So, according to Gauss law, we can write that dN1 del S minus dN2 del S equal to del Q. And this del Q can be written as rho S del S. So, dn1 minus dn2 is equal to rho s, or dn1 is equal to dn2. So from the equation dn1 equal to dn2, we can conclude that normal component of flux density is continuous across the boundary, but the normal component of electric field is discontinuous because En1 is not equal to En2, because En1 is equal to epsilon 2 by epsilon 1 into En2. So in the diagram, the reflection of D or E at a charge of free dielectric interface is given. So E2 D1 sin theta 1 is equal to E epsilon 1 D2 sin theta 2. So this is the case for the previous diagram. And also tan theta 1 by tan theta is equal to epsilon 1 by epsilon 2. The direction of electric field on each side of the boundary is identical with direction of D, because we know that D is equal to epsilon. Assessment: which component of electric field intensity is always continuous across the boundary is we know that it is tangential component. And second question, for a conservation field, which of the following questions hold good is answer A, that is integral of E dot dl is equal to 0. References. Thank you.